Hello everyone, I'm J Wildberger. I'd like to now continue with the previous lecture where we were talking about the relationship between invertible matrices and solutions to systems of equations. And it's this theorem here that we were tackling, and we had gotten part of the way through understanding the connection between these two things. And I want to carry on with that today. So if A is an n by n matrix, then the following statements are equivalent. That first of all, A is invertible. And secondly, that the system AX equals B has a unique solution X in Vn for any B in Vn. Okay, so we started the proof and we recognized that we had to do two things. We had to show that condition 1 implies condition 2. Okay, and we also have to show that condition 2 implies condition 1. The second one is more challenging. So showing that 1 implies 2 was relatively simply done, assuming that A is invertible. We just have an inverse matrix, and then we're able to multiply both sides of that relevant equation to actually solve for x. Now, to get from 2 to 1, so we're assuming that AX equals B has a unique solution, and then we did something that actually kind of conjured up, well, not exactly an inverse, but at least a right inverse for the matrix A. What we did is we looked at the various column vectors, sort of basis vectors, that have all zeros except for a single one in the I spot. We call that EI. And then we solved AX equals EI. So we're assuming that we have a solution no matter what the right-hand side is. So we have some solution, say YI, and then we can put all those YIs together to form a new matrix called capital Y. And that we saw was a right inverse for A. That is, A times Y is the identity. Now that's going to be an important point. So that little argument was important because later on we're going to see that that's exactly the essential sort of technology required to construct inverses of matrices more generally. That is, in higher dimensions where it's not so obvious how to find the inverse of a matrix. Okay, so it's exactly this technology here that we're going to be using. We're going to be finding inverses exactly by cooking up these vectors y1, y2 through yn. By solving the system A, yi equals EI. But we're going to do that in a clever way. Okay, but that's still to come. So we're still in the process here of completing this proof. So we have found this right inverse y, but we're not yet able to deduce that A is necessarily invertible out of that, because just because it has a right inverse, it doesn't mean that it also has a left inverse. Okay, so we're going to need some more arguments today to kind of bridge this this last step. Okay, so we're in the process here. So we're assuming condition 2. We've deduced that this matrix A has a right inverse of Y, and we know that AX equals B always has a solution. So let's carry on now with the argument. So we're going to deduce some more sort of relevant facts in this situation. All right, so let's start by saying that since AX equals B always has a solution, in fact, a unique solution, that's by assumption, we have the special case. We know that AX equals 0 has only the solution x equals 0. So there's also a unique solution if we put the simplest vector on the right-hand side, the vector 0. So this simplified equation, it's a homogeneous equation, AX equals 0. We're basically knowing that this thing always has a unique solution, and that's the solution x equals 0. And now let's think about what that tells us about the effect of a row reduction. Remember, if we started with this equation and we just wanted to, apply our row reduction technology for it, what we would do is we would reduce both sides of an augmented matrix. Now, in such a case, the augmented matrix, let's say augmented matrix for such a homogeneous system starts off with A on the left and the 0 vector on the right. And then we row reduce that. We row reduce it to, let's say, u. And the right-hand side is still going to be 0 because, well, all the row operations are not going to change the fact that that right-hand column is 0. So we're going to end up with u0, where u is in reduced row echelon form. It's necessarily n by n because A is n by n. And since there's a unique solution, it must be every column of U is a leading column. And every column of U is a leading column. So let's have a look. What can it look like? We have this matrix U. We know it's n by n. Okay? We know it is in reduced row echelon form. And we also know that every column is a leading column. So that means every single column has a leading entry, which must be a 1. Okay? There are altogether n such columns, and each of them contains a leading entry. And the other thing that we know is that the leading entries are staggered down to the right. Okay. Now, since the number of rows equals the number of columns, the total number of leading entries, the number of leading entries is n, which is also equal to the number of rows. That means that every row is leading. Every row is leading. In other words, there are no non-zero rows in this matrix. And because the leading entries are all staggered successively down to the right as you move down, it must be that the leading entry in the first column is right at the top, that the leading entry in the second column is second, and that all these leading entries march right down the diagonal of this matrix U till we get to the nth column, and we have the leading entry 1 in that last spot. And everywhere else, there's going to be 0, so I'll just put some big zeros here. So in other words, we're observing that U has to be the n by n identity matrix. That's the consequence, okay? That as a result of our assumption that AX equals B always has a solution, and in particular that AX equals 0 always has a solution, we can deduce that the reduced row echelon form for our matrix A has to be the identity. Now, that's good because we know exactly how or what steps we are taking to go from the original matrix A to this reduced row echelon matrix U, which is just the identity. We know that we're operating by applying elementary row operations. So row reduction involves elementary row operations. And what we're going to do is we're going to analyze these 3 elementary row operations at the level of matrices. In other words, we want to connect the row reduction algorithm, which is sort of just done at the level of rows, with actual matrix arithmetic. That will then be the key to being able to deduce that A, the original matrix, is actually invertible. It doesn't just have a right inverse, it is honestly invertible. Okay, so that's what we're going to do now. We're going to look at elementary row operations as matrix multiplications. Maybe we'll put that there. Elementary row operations as matrix multiplications. Okay, our first row operation was swapping two rows. So let me illustrate it by an example, which is a little bit clearer. So suppose that I have a matrix, 1, 2, 3, 4, 5, 6, 7, 8, 4, 3, 1, 9, and 2, 1, 6, 6, let's say, okay? And suppose that I want to swap. I want to go from here. I want to interchange row 2, let's say, with row 3. Okay. So I want to go to 1, 2, 3, 4, 4, 3, 1, 9, 5, 6, 7, 8, and 2, 1, 6, 6. How can I do that? By matrix multiplication. Okay, so claim this is accomplished by multiplying on the left by the following matrix. I'll start with the identity matrix, and I'll change it just in a second, so don't copy this down exactly yet. So we're starting with the identity matrix, okay, and it all has all these zeros, which I usually don't write, but I will just in this case here. Okay, that's the identity matrix, but we're not going to use that. What we're going to do is we want to swap the second and the third row. So what we're going to do is we're going to take these two diagonal elements in the second and third positions, okay, second and third positions, and I'm going to change them. I'm going to change them to zeros. And so I'm sort of working on this little 2 by 2 thing here. And correspondingly, I'm going to change these off diagonal things to ones. I claim that multiplying by this matrix on the left will interchange the second and third rows of whatever matrix you're multiplying. So let us check that. Okay, so here is 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1. And I'm going to multiply by 1, 2, 3, 4, 5, 6, 7, 8, 4, 3, 1, 9, and 2, 1, 6, 6. Now, I'm going to also teach you at the same time a slight variant on how to think about matrix multiplication, which is useful. So up till now, I've told you that we should concentrate on sort of doing it one column at a time, okay? But it's also possible to do it one row at a time, okay? And for this particular application, it's actually more insightful to think about it in that point of view. So we're going to evaluate this product one row at a time. Let's think about this first row. How do we get the elements in the first row of this matrix? We get it by taking the first row here and multiplying that first row first by the first column, and then by the second column, and then by the third column, and then by the fourth column. That's how you go along the first row of the end result. So what is that? If you multiply any one of these columns by 1, 0, 0, 0, what are you doing? You're just picking up the first entry in that column, because it's 1 times the top entry and then plus 0 times all the other entries. So you're going to get over here 1, 2, 3, 4. How about the second row? So the second row, I'm going to get that. I'll give myself a little bit more space here. The second row is going to be obtained by taking the second row over here and multiplying it by each one of the 4 columns. Let's see what happens when you do that. Okay, so 0, 0, 1, 0 times the first column, 1, 5, 4, 2. That's going to pick out the 4. We're only picking out the 4, the third element, because the 1 is in the third spot. So it's 0 times 1 plus 0 times 5 plus 1 times 4 plus 0 times 2. So we're getting a 4 there. For our next column, we're going to get a 3, and then a 1, and then a 9. We see that what we're doing is we're copying the third row into the second row position. And something similar happens when we go to the third row over here and multiply by the third row over here, which is 0, 1, 0, 0. When we multiply all columns by that, we're picking up the second entries of each of those columns, 5, 6, 7, 8. And finally, when we use this last row, we get 2, 1, 6, 6. So that verifies, okay, that's exactly how we go from this matrix to this matrix. If we just worked in the language of matrix arithmetic, we can do this row operation, this elementary row operation, by multiplying on the left by this, you could call it sort of like an elementary matrix. Okay, it's got zeros, mostly zeros, and a few ones, and the ones are mostly along the diagonal, except that just in the two spots that correspond to the positions of the rows that we want to swap, we've changed where the ones and the zeros are. Now I want to make one more important observation about this matrix E1. Note that E1 squared is the identity matrix. Okay, in other words, if you take 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, well, sorry, 1, 0, 0, 0, 0, 0, 1, and you multiply that by itself, okay, then what you get is the identity matrix, in this case, the 4 by 4 identity matrix. And that has the important consequence that therefore E1 is invertible, because it has a left inverse, which is E1, and it has a right inverse, which is E1. Okay, so there's an obvious generalization to this. If we are in n by n case, then to swap rows I and J, we have to use a matrix, maybe E1, which has the following form. Okay, it's a little bit more challenging to write it down. So there's ones along the diagonal, okay, until you get to the I, maybe in the Jth rows and columns. Maybe I would be up here and J would be here, okay? So these sort of Ith row and Jth row and the Ith column and the Jth column, okay? And those two rows and two columns are determining four positions, these four positions here, okay? And the thing about this matrix that we're using is it's like the identity matrix, except in exactly these four positions, where there's a 0 here and a 0 here instead of being in the instead of having ones. And on these positions, there are ones. Okay? So that's what it looks like in general, and it still has the property that E1 squared is the identity, in this case, the n by n identity. Great. So we have now dealt with the first kind of elementary row operation, which is to swap two rows. Now, what about adding, say, a multiple of one row to another? So, for example, suppose that we want to take the same matrix 1, 2, 3, 4, 5, 6, 7, 8. What was it? 4, 3, 1, 9. 4, 3, 1, 9. 2, 1, 6, 6. Okay. 2, 1, 6, 6. Okay. So suppose, for the sake of argument, that we were in the middle of a row operation and we want to get rid of this 2 here. Okay. So what we want to do is we want to replace row 4 with row 4 minus 2 row 1. Okay. How are we going to do that? So we want to end up getting 1, 2, 3, 4, 5, 6, 7, 8, 4, 3, 1, 9, and the last row minus 2 times the first row. So that's 2 minus 1 is 0, 1 minus 4 is minus 3, 6 minus 6 is 0, and 6 minus 8 will be minus 2. Okay. So how can we do that at the level of multiplication by a matrix? So we want to put some matrix over here that will affect this row operation. Okay, so what we're going to do is we're going to more or less use the identity matrix, in this case 4 by 4, but we're going to modify it again like we did in the previous case. We're going to modify it a little bit. If we just did this, we would just not do anything, but we want to ensure that the last row that we're getting, okay, this last row here, is obtained from these rows here by taking minus 2 times the first row and adding it to the fourth row. So how are we going to do that? Well, in order to deal with this row, it's crucial that we just look at this row here. It's a question of putting the right things in there. And what we're going to do is we're going to change this 0 into a minus 2. Okay, great. So we found this new elementary matrix. Let's call it E2. Okay, this matrix E2 has the property that when we multiply on the left by it, it has the effect of adding minus 2 times the first row to the fourth row. So it's giving us one of these elementary row operations of the second kind. And as before, we're going to note that this thing has an inverse. E2 is invertible, and its inverse is, well, I'm going to leave you to check this. Okay, the inverse is, if you want to undo adding minus 2 of row 1 to row 4, the way you undo that is by adding plus row 2 to row 4. So in other words, if I put a 2 here without a minus sign, then that is the inverse of E2. So in either order, you multiply those two things, you get the identity. So I'll leave it to you as an exercise to check that E2 times E2 inverse really is same as E2 inverse times E2. It really is the identity matrix in this case. Okay, and in general, you could do some kind of similar thing for the n by n case. Okay, it's really the same kind of thing that we're looking in this case here. This is like the ijth entry. Okay, the ijth entry. The effect is to add. So this is actually in the 4, 1 position. So we're adding minus 2 times the row j to row I. So that's how you would generalize that to the n by n case. And our third kind of row operation is perhaps the simplest one, multiplying a row by a non-zero scalar. Okay, if we want to 4319, 4319, and 2 something 2166. Okay, suppose that we want to multiply this third row by 3. Okay, so we want to go to 1, 2, 3, 4, 5, 6, 7, 8, multiply this third row by 3, 12, 9, 3, 27, and leave the other ones where they are. So how do we do that? What do we have to multiply over here by? Well, it's actually pretty simple. We're just going to multiply by the identity matrix modified so that the third entry along the diagonal is 3. Okay, and so we could call this thing E3, and pretty clearly the inverse of E3 is E3 inverse, which is the same kind of thing, but having the inverse of that multiple in that same position. So what we conclude then is that we've concluded two things. So therefore, elementary row operations can be affected by multiplying by elementary matrices on the left. And each one of these and each of these is invertible. That's great, because that then sort of is the extra piece of understanding that we need to deduce back to where we started, okay? To deduce that this matrix A that we started is actually invertible. So I remind you that we were, at this stage here, we were talking about this relation here, so that we're assuming that we've gone from A0 to U0, where we've row reduced and U is in row echelon form reduced, and that we've deduced had to mean that we actually get the identity matrix. And so what we're now observing is that this process of row reducing A is affected by multiplying on the left repeatedly by different elementary matrices, exactly of the three kinds that I've just outlined. And crucially, each one of those is invertible. So the consequence of that is that, so row reduction from A to U is, okay, we're starting with A, and then we're performing row operations, and they correspond to multiplying on the left by some elementary matrices, maybe E1, then followed by E2, then followed by E3, maybe all the way up to EK. So maybe we've done K operations altogether. And the effect of that is that we get U, which was the identity matrix. But then we can observe that, but now we can take this equation and we can solve for A, because we know how to invert these matrices E sub 1 up to E sub k. They're all invertible. They all have inverses. So if we multiply by the inverses of the EKs successively, so then multiplying by the inverses of first EK and then all the way down to E1, we get matrix A is, so first we multiply by EK inverse. I'll put it over on this side. And then we multiply by the next one, EK minus 1 inverse, all the way down to E1 inverse. And it's this expression that allows us to deduce that A is invertible. So A is invertible because it is the product of invertible matrices. We've shown that the elementary row operation kind of matrices, they are all invertible. We've looked at the three different kinds and shown that each of those three different kinds are invertible. And so that means that the product of any number of them will also be invertible, because the product of invertible matrices is invertible. And that is why this matrix A, which we started off just assuming that it had the property that AX equals B has a unique solution, that we can now deduce that it's actually invertible. And as a consequence, okay, I'll just say it. And as a consequence, its inverse is that matrix Y that we found earlier, the right inverse that we found earlier. Here, this matrix Y that appeared here, that was then going to be the inverse of A. Okay, so that finishes this sort of story. So we've kind of explored the rather rich story, and it's actually quite a little bit subtle. Okay, definitely the most subtle aspect of this first course in linear algebra. This is the heart of things right here, actually. Okay, so if you understand this theorem and the various implications and connections, then you have a pretty good understanding of important aspect of linear algebra. This is really close to the heart of things because, as I've said, inverting matrices is close to being the essential computation in linear algebra. Okay, great. And along the way, because our discussion has been rather extensive, along the way we've actually found this procedure for actually finding the inverse. This Y matrix that we cooked up this way, and I remind you that that was by solving A, yi equals EI. That was actually a way for us explicitly to use the solution of systems of equations technology to find the inverse of a matrix. That's what we're going to talk about next time, how to apply that systematically to find inverses of matrices in higher dimensions.